So thanks a lot for giving me this opportunity to present my work, which I have done with Professor Vikram Rentala. So far in this workshop, we have seen like the structure of dark matter, right? Starting from galactics, like the galaxy cluster scales, and then how it is distributed in the galactic scale. So my work is basically about what if within a galactic scale, the dark matter has some granularity in the form of, let's say, primordial black holes. So if your dark matter, a fraction of dark matter is made up of primordial black holes, then what will be the observational signatures of those primordial black hole dark matter? So we know that the primordial black holes are not formed due to the stellar death, but they are formed in the very early universe due to the density fluctuations. And throughout the history of universe, they will evolve, they will accrete matter. And my work is basically about those primordial black holes will be basically a constituent of the dark matter in the today's epoch. So what is those signatures which will be induced by primordial black holes? So we know that there are certain observational signatures of PBH dark matter. Some comes from, if the PBH is very tiny, then they will evaporate due to the Hawking radiation. So there are certain constraints on the parameter space of PBH. So in all these panels, there is a y-axis, which is the fraction of dark matter in the form of primordial black hole. And the x-axis, you assume a monochromatic mass function. That means all of the PBHs have the same mass. So in that parameter space, there are constraints from evaporation, there are constraints from microlensing, and there are constraints from gravitational wave due to the collisions of PBHs. And there are constraints if you assume there are certain fraction of PBHs along with the stars in a certain galaxies, then they will transfer some energy from dark sector to the visible matter. And then if the PBHs are very massive enough, then they will accrete matter and they will create a radiation, and which you will be able to detect in X-rays or radios. So my work is basically specific to the microlensing part. So there are two aspects of microlensing. One is the brightening of a star due to the microlensing effect. Another one is the shift. So whatever the constraints that you are seeing right now is due to one aspect only, which is the brightening of the star, the apparent brightening. So we ask a very simple question that can we detect or exclude the existence of these primordial black hole dark matter with the precise measurement, astrometric measurement of stars in our Milky Way by the Gaia space telescope. And what we found is on this parameter space, you can actually either set constraint or you would be able to detect these PBHs. If the mass range of PBHs are something like 0.4 solar mass till something like 10 million solar mass. And the typical signature that would be shown by PBHs in these Gaia space telescope would be the astrometric microlensing signal. So I'll be explaining quickly what this signal would be. So basically, if you look at a stellar trajectory in a sky and assuming that it is moving in a straight line along this blue direction, and there is a lens in the foreground of this star, so this star is in the background, then because of the gravitational effect of this foreground lens, what you will actually see is not the blue trajectory, but you will see a distorted trajectory, which is shown by the colored dots over there. And the color signifies what will be the apparent brightness in the star. So these are the two effects, the apparent shift in the trajectory and the brightening. So one, which is the apparent shift in the trajectory, is basically astrometric microlensing, and the apparent brightening is the photometric microlensing. The apparent shift is basically the scale of that shift will depend on these three quantities. One is what is the mass of the lens, of course, because if the gravity is huge, then it will bend light in a large amount, and hence the shift will be larger. And at the same time, it depends on the distance of the source, which is ds, and where the lens is lying in between you and the source. So that scale is basically called Einstein angle. So what we did is we studied these trajectories, and we asked this question, okay, what Gaia is going to give us? So as an output of Gaia telescope, what it gives is more than 1 billion trajectories of stars, which is like around 1% of the stars in the Milky Way. And the precise positions, the astrometric precision of each measurement is going to be something like 0.1 milliarc second. And it is going to give you like 35 individual positions of star within a 5 years. So that is the kind of an outcome of Gaia Space Telescope. So we asked this question that if our galaxy includes these trajectories, and you assume that the dark matter, there is a fraction of dark matter which is primordial black holes, which is granular, then those PBHs will distort some of those trajectories. So how many those trajectories will get distorted and would be observed by Gaia Space Telescope? So we did a kind of a characterization of the astrometric microlensing signal, and here it goes. So basically, this is a trajectory of a star, and it is distorted, but the fraction is very small, the fraction by which it distorts. So I subtract that fraction, and that is what I'm plotting here on the y-axis. So this is the amount of distortion that this trajectory is experiencing. And all I have done in various signals over here, I have just changed the mass of the lens only. Okay, so you can see that the blue trajectory that has a very small mass, which is like something like 0.25 solar mass. And this is the kind of a detection threshold by Gaia. So your signal, which is this y-axis delta, the shift, has to be above this horizontal line so that it can detect the signal. So if the mass is like something like 0.25 solar mass or below that, then this blue trajectory would come up to this threshold, but that duration for which it is above that threshold will be very small. And as I showed you that Gaia is going to give you on average like 35 measurements within 5 years, which turns out to be 52.2 days. So if this duration is less than that, then you are going to miss that signal. So that is the kind of a signal which we defined as short duration lensing event. And we assume that it is hardly going to be observed by Gaia, although it is not strictly true. The second kind of event is this magenta, where the duration of the event is within this vertical bar, which is the observational period of Gaia, which is 5 years. And all those signals will see this maxima during the trajectory. So all those trajectory we call as intermediate duration lensing events. And we consider the maximum shift as the detection criteria for an event. And then at the end, you can see the large signal event, which is for example, it is for 10 solar mass. And for those kind of a signal, the observational window will only see a part of the signal. So that is not going to be exactly the signal. So what you will get as a signal is really the difference in the shift in the signal. So that is how we define third kind of signal, which is long duration lensing event, for which the duration is much larger than the lensing event. And that is what this would become. So basically, from all these analyses, what we wanted to get at the end, that how far a star can be from the lens so that it would give you a signal which is above the detection threshold. So once we have that, then we can calculate what is the sensitive area around each lens corresponding to each different kinds of signal. And that will give you the maximum threshold beta angular separation within which a star has to lie in order to give you a signal in Gaia. And on top of it, we know that that lens is going to move. So if the velocity or the relative velocity of the source and the lens is v, and observational period is t obs, then divided by distance of the lens will give you how much angular separation it is going to travel in the sky. And that will basically sweep an area in the sky. And that is going to be the sensitive area around each PBHs. Okay. So what we did is we considered a patch in the sky, and we counted in that patch how many PBHs with a particular sensitive area would lie. And then we ask, what is the probability that a star will lie in the yellow area? So that is how we calculated what is the probability of each star to be lensed by a PBH and will be detected by Gaia. So we get a distribution of lensing events. So depending upon what is the location of the star in the sky, distance, and how bright that star is, we get a particular distribution of the lensing event, that how many number of lensing events you will be observing, that the Gaia will be observing. So this is just an example for 14 solar mass, and assuming all the dark matter is PBH. But we scan over all the fraction and all the possible mass of the PBHs, and we get a sensitivity curve of Gaia for the detection of PBHs through astrometric microlensing. And you can see that Gaia can actually observe like as thousands of trajectories that will be bent by the PBHs if you assume that all of the dark matter is PBH. And the maximum sensitivity lie around tens of solar mass. One of the interesting features that come out from here is, you know, that if you assume that all the LIGO-Virgo events, the black hole merger that has been observed, they are from PBHs, then the parameter that you need in order to fit is basically lies somewhere here. So there's a 2 sigma contour for that. Now, if Gaia exclude that region, that would exclude fully the possibility that what LIGO-Virgo has observed is really the PBH black holes mergers. So that is the first thing. So in summary, there are basically 4 outcome of our work that is main. One is we predicted how many number of astrometric lensing events that Gaia is going to observe if you assume PBH is a dark matter. And the second is we characterizes the lensing event signals in 3 parts: SDLEs, IDLEs, and LDLEs. So the signatures will be very different. And in the third, we come up with a pipeline which can actually give you, if you assume any Gaia or the stellar catalog, and you assume any dark matter hypothesis, like you assume different profiles or different compact granular dark matter hypothesis with various velocity distribution, that gives you the how many number of lensing event that Gaia will be observing. At the end, this is the sensitive area that Gaia would be sensitive to maximum under our hypothesis.
Thanks, Himanshu.
Thanks a lot.
Questions and comments? Yes, please.
Very nice talk. So my question is, on this plot, what is limiting Gaia from setting constraints to the left and to the right?
Yeah.
What are the limitations?
Right. So if you go to the lower end, what happens is, as I told you, that the shift depends on the Einstein angle, and that Einstein angle is square root of mass. So if you reduce mass, then the shift will be small and it will go below, like, let's 0.2 milliarc second. Okay, so that is the lower cutoff. The higher cutoff comes because of the fact that if your mass is very large, then the number density of the PBHs will go down. It's like density of dark matter divided by the mass of the PBHs, right? So there will be less probability that a PBH will be in front of a particular star. So this basically goes down because the probability of lensing goes down.
Okay, thanks.
The cross section for lensing actually goes inversely with mass, in proportion to mass, right? Because Einstein angle is proportional to root m. So if you reduce the number density, the cross section will still increase. The total lensing probability will still remain the same.
No,
because though the number goes down by m, the cross section increases by m.
Yeah, so if you look at this sensitive area dependence, so it has this beta threshold, and in various limit, it sometimes, so if the mass is very large, then it goes as theta e, which is square root of m. So square root m divided by m, it becomes 1 over square root m. So that is why as you increase mass very large, the ultimate probability is going to go down. And the lower mass range is just because of the sensitivity or the whatever the uncertainty in the Gaia would be. So that that basically kills the lower end of the sensitivity.
Okay.
Yeah.
Thanks.
So you've shown forecasts for what you would get with Gaia after 5 years of observing. Do you know what limit you would be able to set with? I mean, I don't know how much data they've published already. What would the limit look like? And when like, do you plan to do like do you plan to check the real data as well?
Yeah.
Soon?
So basically, this exclusion is on the basis of 5 years data. Actually, it is on the basis of 34 months of stellar observations, but we kind of extrapolated it to 5 years. So roughly speaking, so there have been, recently there was a recent paper which basically studied this for 10 years of observation. And for that, it goes like as small as something like below 10 power minus 4, so somewhere here. So that will be like the ultimate sensitivity, like 0.001% of the dark matter.
No, but I mean, what would it be like with current data?
So in the current data, they haven't published the time series data yet. Okay, so that will be like DR4. So till now we have just DR3, the third data release. So when the time series data will be up, then we will be able to see what is actually the exclusion that would look like. So yeah, I mean, it will be kind of contaminated with the binaries, and then that is the main concern, and that basically will affect this part of the exclusion mostly.
Very nice talk. Thanks. So I had a question. So can you try to sort of boost the signal by maybe, I don't know, combining like stacking or combining along directions with high densities, like, maybe high towards satellites or something like that?
Definitely. So
Versus
if you look at the distribution of our lensing event, and let's look at the sky map. So it is maximum, the number of lensing event is going to be maximum for the stars which are at the galactic plane, because and that is maximum towards the center of the galaxy. But of course, towards the center of the galaxy, there is a trade-off. As the star goes towards the center, there is a higher probability that the lens will lie within that, but the accuracy with which Gaia can actually measure that goes down. So if you look at this curve, that basically peaks somewhere around 5 or so. So you can't go beyond 5, a few kiloparsec in order to look at these kind of lensing events. Yeah.
Okay, so thanks. So we'll move to the next talk. Thank you very much.
Thank you.